In this video, we're going to introduce mass spectrometry. So, what is a mass spectrometer? It is an instrument that we use for molecular analysis. So when we want to know information about entire molecules. And the main data that we get from it is data on the molecule's mass. So what are our goals when we're using mass spectrometry for molecular analysis? So the first thing that we want to determine is the molar mass, or the molecular mass of our molecule. And the second thing is we want to determine the molecular structure. So we want to know how those atoms are connected. And these are both things that we can determine from our mass spectrometer. So the data that we get from a mass spectrometer is a graph that on the x-axis has mass per charge, m over z, which really we can think of as just the molecular mass. And on the y-axis, we have the relative abundance in a percent. And what these graphs look like is they have peaks, with the highest peak being at a relative abundance of 100, and all the other peaks being smaller than that. So a graph could look something like this, with here we have 5 peaks. Usually there's a lot more smaller ones in random places. And the two main peaks that we want to be able to name is the base peak, which is the peak that reaches 100% relative abundance, and then the peak furthest to the right, which we label M+, and that is our molecular ion. Understanding a little bit about how the mass spectrometers work will help us be able to analyze the graphs more easily. So there's three main parts to our mass spectrometer. The first is the ionization source. The second is the mass analyzer. And the last is our detector. So let's use benzene as an example of how this system works. So our benzene molecule enters our mass spectrometer, and at the ionization source we have a way to ionize the molecule, and usually that is through electron impact. So electron impact, we take an electron and shoot it at our benzene, and then the electron knocks off one electron, and it leaves itself. So we have two electrons leaving. The electron that came into the system, and then it knocked off one electron, and two electrons left. And that leaves our benzene having a net positive charge. So for benzene, that would be a positive charge, and then a radical on one of the carbons. And then this enters our mass analyzer. And what the mass analyzer does is it separates molecules by mass. And then the detector takes those separated masses and reads them onto our computer. So if we had benzene, it would give us a signal of some relative abundance percentage of the molar mass of benzene, which is 78 atomic mass units. So since our mass to charge ratio is on the x-axis of our graphs, of our output graphs, our mass here is 78, and our charge is positive 1. And for generally all types of mass spectrometry, the most common charge will be +1. So that's why we can say that the x-axis is basically just the atomic mass. And so at 78, we would have a peak for our benzene. So let's say our molecule that we're looking at is propane, and we wanted to determine where the major peaks would be. So propane has 3 carbons, and it has 3 plus 3 plus 2 hydrogens, so 8 hydrogens. And carbon has an atomic mass of 12, hydrogen has a mass of 1. So our molar mass for propane would be 44 atomic mass units. So when we have our electron impact the propane and 2 electrons leave, we could get propane with a positive charge, and the mass would be 44. So we would expect a peak at 44 atomic mass units. But when we're using electron impact as our ionizer, electrons have a lot of energy. So in addition to breaking off another electron, they can also, in some cases, break chemical bonds. So if we have our propane, and if we were to draw all of our hydrogens, if we have an electron with enough energy, the electron could potentially break a bond, and it could knock off one of these hydrogens, which would then give us the compound of propane with a positive charge. And since there's a positive charge there, it'll still show up in our detector, because positive charges are what we're detecting. We can only detect molecules with positive charges. But if it can break a carbon-hydrogen bond, it could probably also break a carbon-carbon bond. So if we have our propane and our electron comes in, let's say it attacks the carbon-carbon bond. We would have a carbon with 3 hydrogens and a positive charge if we split the carbon-carbon bond here. And then we would also have a ethanol or an ethane, but one of our sides would only have 2 hydrogens on it and then a positive charge. So since both of these are positive charges, they would still show up in our detector. Now let's see what these masses would be. So for the propane that just lost a hydrogen, the initial mass would be 44, the total mass, but we're losing 1 hydrogen. So that would have an atomic mass of 43. Now for when we're breaking the carbon-carbon bond, we have a carbon and 3 hydrogens, so that would be 15 atomic mass units, and then here we have 2 carbons and 5 hydrogens, so that would be 29 atomic mass units. So based on this fragment analysis, we can assume that there will be peaks at 44, 43, 29, and 15. And sure enough, here's an accurate spectrum. So we expected to see a peak at 44, 43, 29, and then at 15. And we see all of those peaks. And there's additionally a bunch of other peaks, and if we wanted to, we could theorize what fragment caused every single one of those peaks, but that's not necessary to identify a compound. So now let's try an example where we're given a spectrum and we have to find the formula of the compound. So we're given that the molecular mass of the compound is 86, and we're given that it's a hydrocarbon, so it only has carbons and hydrogens. So first we need to see how many carbons we could potentially have. So carbon's mass is 12, so if we had 5 carbons, that would be a mass of 60. So if it was C5, we would have to have 26 hydrogens to get up to a total mass of 86. And that's not possible, so we have to have more than 5 carbons. If we have 6 carbons, that would be a mass of 72 just for the carbons. So C6 and then 86 minus 72 is 14. So H14, which is definitely a possible compound. Now if we had 7 carbons, that would be a mass of 84, which would mean we only have 2 hydrogens to make a total mass of 86. And that's not a real possible compound. So we know that the compound must be C6H14, which is hexane. And we can look at the fragments to confirm this. So C6 could break in a variety of places. Let's look at the peak 57. How could we get that peak? So 86 minus 57 is 29. So our chunk lost 29 mass. So 2 carbons would be 24, and 5 hydrogens would make 29. So the chunk we lost could be C2H5. And if we lost 2 hydrogens from our hexane, that would break off a chunk of C2H5, leaving a mass of 57. And then our mass of 29 here can also be accounted for in the graph. And if we instead split our mass in half, we would have 2 equal pieces, both with masses of 43, which accounts for our peak of 43. In this next example, we're given 2 spectra, one of 2-methyl 2-pentene and the other of 2-hexene, and we're supposed to figure out the difference. So first, let's draw the 2 compounds. So 2-methyl 2-pentene looks like this, and 2-hexene is a hexane with an alkene on the second carbon. So looking at the spectra, the major difference we see, they both have masses of 84, so that's the same, but the peaks for 69 and 55 are different. On the top graph, the 55 peak is smaller, and the 69 is larger, while it's switched on the other. So for this one, we're going to be looking at the fragmentation patterns. So when we're looking at how molecules will fragment, we have to note that the weakest bond will break first. So our alkenes aren't going to break because we know that alkenes are stronger. Carbon-carbon double bonds are stronger than carbon-carbon single bonds. And then we can also think about alkenes as having high electron density. So there's a lot of electrons around the alkenes, and so that makes the bonds between the neighboring carbons to the alkene carbons also stronger. So this bond here, since one of the carbons is part of the alkene, will be a stronger bond than this carbon-carbon bond at the end, since there's no alkene carbon in the bond. So when we're looking at the bonds that will break, we want to look at the bonds that have no bonds to an alkene carbon. And so for 2-methyl 2-pentene, that bond is this bond at the end. So we have a methyl group that will break off. Whereas for 2-hexene, we could break off an ethyl group, or we could break off a methyl group. But it's also important to note that larger groups that break off will generally be more stable. So since we can break off the ethyl group, that will be more favorable than breaking off just the methyl group, since ethyl groups are larger. So for 2-methyl 2-pentene, it looks like after we break off that methyl group, we will be left with a positively charged group here, along with our methyl. And then for our hexene, we'll be left with a positively charged ethyl group as well as our alkene. And so if we look at the masses of these, so we lost 12 plus 3, so we lost 15 from our 2-methyl 2-pentene, so this will have a mass of 69 as our most favorable fragment. And then for the hexene, we lost 5 hydrogens and 2 carbons, so that's 29, and 84 minus 29 is 55. So our largest fragment here is 55. So from that we can determine that 2-methyl 2-pentene will have a larger group at a larger peak at 69, so that matches our top graph, and 2-hexene has a larger group at 55, so that matches our bottom graph. Here's another example that you can pause to solve on your own. So we're given 2 spectra. One is methyl cyclohexane and the other is ethyl cyclopentane. So let's draw those compounds. First we have methyl cyclohexane and then ethyl cyclopentane. So the important things to note here is that in general rings are stable and rings don't want to break. So when we shoot our electrons at our molecules, the first thing to break off is anything that's sticking off of a ring. So for methyl cyclohexane, we'll break off our methyl group, and for ethyl cyclopentane, we'll break off our ethyl group first. So what those will leave behind is a hexane with a positive charge and a pentane with a positive charge. So if we add up the masses of those, we have 6, or we can rather think about what we lost. So for methyl cyclohexane, we lost a carbon and 3 hydrogens, so we lost 15, which means, assuming our mass was 98 to start, losing 15 would mean our major peak would be at 83. For ethyl cyclopentane, we lost 2 carbons and 5 hydrogens, so that's 29, meaning 98 minus 29 will have our group be primarily at a mass of 69. So based off that, we can look at our graphs and we can look at our highest peaks and say that ethyl cyclopentane must have been our top graph and methyl cyclohexane must have been our bottom graph.